Field robots for challenging domains such as forestry face several technical challenges inherent to their ability, or lack of it, in operating under the unstructured, harsh, and dynamic nature of such outdoor environments. This presentation presents the first steps towards a theoretical framework which guides the development of affordable field heavy-duty robots. This video will shed some light in the development of such robots for the forestry domain, introducing the Ranger as a peaceful and harmless heavy-duty companion. Hello, my name is Micael Couceiro. I am the CEO of Engenharios and coordinator of a few projects populated by many outstanding researchers, developers, and academics who tirelessly contribute to the deployment of innovative and disruptive mobile robotics solutions. Engenharios is a highly interdisciplinary team of researchers experienced in the full chain of mechatronics development. Most of its experience falls in the full development of unmanned field robots, namely for ground, aerial, and underwater applications. Although only created in 2014, the company already designed several solutions within the domain of intelligent systems and robotics that are currently available in the market. These and other achievements led to an increased visibility over the past years, making them the coordinating company of many R&D projects co-funded by the Portugal 2020 program and many others supported by the private industry. Propelled by this experience, built in close collaboration with academia and stakeholders, the team possesses a unique perspective on the field robotics domain, which revolves around the development of robotic technologies for difficult, repetitive, and unpleasant tasks carried out outdoors and under harsh conditions. Agriculture, forestry, and constructions are only a few use cases examples where field robotics has a role to play. And while robotics has been key in the fourth industrial revolution, or Industry 4.0 as they call it, these challenging domains have been left nearly uninhabited by robots. The reasons being the unstructured and unknown environment robots need to be deployed on, the rough terrain traversability inherent to such environments, the needed level of reasoning and planning under a high level of uncertainty, and the extremely challenging perceptual conditions felt. I had the opportunity myself to work on a series of projects within the field robotics domain, some harder than others. These include the development of pervasive localization architecture for autonomous lawn mowing, path planning and navigation for autonomous solar panel cleaning, leader-follower architectures for aquatic robots, and the most challenging one I had the pleasure to work on, at least until now, the development of forestry robotic systems, be it for the removal of forestry fuel for wildfire prevention or the removal of undesired vegetation around critical infrastructures, including railways. Vegetation clearing is a quite demanding task, influenced by the irregularity of the terrain and the density and type of vegetation at stake. For these reasons, proper selection of the machine, including its attachment, is crucial and can lead to very profitable outcomes in the end. Heavy-duty machines equipped with forestry mulcher attachments, such as compact track loaders, are capable of mowing down hectares of large brushes and even small trees with no effort in a few hours. This also implies that these machines are quite dangerous and safety measures need to be taken into account, especially when having autonomy in mind. In a nutshell, the core element of these projects is called Ranger. If we were to develop a disruptive, autonomous, and ecological machine like this from scratch, we will need to address several disciplines, ranging from the base ones, such as mechanics, electronics, automation, and even hydraulics, to the most advanced ones needed to achieve the necessary level of autonomy, such as mechatronics, computer vision, computer science, control, and naturally robotics. For this reason, and even though the literature presents a few out-of-the-box heavy-duty robots, many are at low technology readiness level or are not all-encompassing at all. This makes it currently impossible to acquire a commercial robot capable to be deployed in forests and other challenging domains. The cost of developing in-house field heavy-duty robots, the lack of multidisciplinary teams involving end users and stakeholders, and the broadly adoptive passive nature of most envisaged solutions makes the current efforts insufficient to enable future market development. Therefore, to bypass some of these struggles and introduce new solutions in the market faster, A step toward the right direction falls on the idea of developing plug-in solutions comprising sensors, controllers, and sometimes even new actuators, and applying those into existing heavy-duty machines. Nevertheless, to do so, a set of procedures need to be taken into account, starting with the understanding on how these human-operated machines actually work. Nowadays, heavy-duty machines such as trucks, buses, mobile hydraulics, and others are more automated than they have ever been in the past, just like our own cars. These are filled with electronic components. By understanding how these components communicate with each other, robotization is just one step ahead. In the early days of controller area networks, or CAN for short, every device manufacturer interpreted messages in its own proprietary way. This means that Bobcat machines will be unable to communicate with John Deere ones and the other way around. However, the J1939 standard brought some order to this mess and reduced the development effort significantly by presenting itself as the most important standard in the heavy-duty machine industry. With the wide adoption of these methods and the rise of heavy-duty telematics, J1939 has been playing an increasingly important role in the market for connected vehicles. One of the driving forces behind its worldwide success has been the increased adoption of electronic control units, or ECUs, which are the embedded systems within the machines in charge of controlling its electrical systems. Engine control module, powertrain control module, transmission control module, brake control module, central control module, and many others are only a few existing ECUs within a given vehicle, meaning that if they all speak the same language, the better. Because of its success, the J1939 standard defines more than 1,500 frames and more than 100 ECU IDs for highway, agriculture, forestry, construction, and marine equipment. In brief, J1939 is a high-layer protocol using CAN as its basis, but only considering a few layers of the 7-layer OSI model. The physical layer describes the electrical interface to the bus. The data link layer describes the rules for constructing a message, accessing the bus, and detecting transmission errors. At last, the application layer defines the specific data contained within each message sent across the network. For instance, J1939 frames may contain information about the engine speed. And if we were to explain J1939 messages, we could state that those are basically CAN frames in the extended frame format, where the frame ID has 29 bits. Among these, we would be able to easily identify one of the most important elements in the message, the parameter group number, or PGN. The PGN serves as a unique frame identifier within the J1939 standard, which is often the same regardless of the machine manufacturer. For instance, the PGN 0F004, or in decimal 61444, is often used to communicate data regarding the electronic engine controller 1, presenting the actual engine percent, torque, and the engine speed. If we know this, then it is just a matter of time until we can fully understand messages exchanged between ECUs and, if robotization is the objective, to hack the system by introducing a new CAN-enabled component able to interpret J1939 messages and control certain units, such as the hydraulic systems and other actuators. Put it differently, a bridge can be built between the J1939 standard within a given heavy-duty machine and robotic standards, such as the Robot Operating System, or ROS. Yet, being able to communicate with a machine is only a first step in its robotization. Human perception, cognition, and skills are hard to match, especially when dealing with unstructured and challenging tasks requiring adaptation and learning. Humans excel on analysis, intuition, problem-solving, and visual perception. Furthermore, highly experienced individuals in the field can perform outstanding stunts hardly achievable by non-experienced humans and definitely not by the current state of field robotics research. For robots to match humans under these challenging domains, certain guidelines need to be employed when building this new generation of affordable field heavy-duty robots. prioritizing the research and technological developments revolving around the perception-action coupling. If humans are the center of this benchmark, then we should start from human-centered studies. James Gibson, born in 1904, was an American psychologist and one of the most important contributors to the field of visual perception. One of his major contributions was entitled as The Ecological Approach to Visual Perception, where he was highly criticized for cognitivism over behaviorism, favoring direct perception and direct realism. Gibson's theory of direct perception states that the environment contains all the information needed to specify its properties. Hence, perceiving these properties is a matter of detecting the information available in the environment. This bold vision at the time led many to follow his concepts and ideas, and applying those to study how perception and action regulate the human performance. Perception implies the ability to read the environment and extract information out of it, thus providing affordances or action possibilities to the cognitive system. The action then implies the ability to select the best affordance and act in the environment in order to fulfill a given task. Within a robotics perspective, perception is crucial for the decision-making, be it for path planning, navigation, and overall operation. Artificial perception in robotics is intended to answer two questions: where am I, and what is that? Robots need to be aware about their location, and while it is easy to some extent on structured environments where artificial landmarks can be deployed, such as QR codes or even wireless beacons, the same cannot be stated for outdoor environments. GPS or GNSS-based technologies, when coverage is available, still lack the needed accuracy and precision. Beyond localization, robots need to be able to extract information from the environment. Humans usually do this by exploiting their senses, including sight, hearing, touch, and smell. Roboticists have been highly active in the domain of biomimetics, and mimicking these senses has been one of their main challenges. However, existing solutions, including camera-based ones, still fall behind their biological counterparts, being susceptible to many sources of noises available in the environment. If we were to divide the existing challenges in perception into categories, we could address sensing and perception separately. At the lower level, sensing is affected by the noisy nature of the environment. Each sensor is affected differently. Cameras and lidars, for instance, as optical sensors, are greatly affected by fog, rain, sun exposure, and others. Ultrasound sensors and radars can overcome some of these constraints, though at a higher cost and still with lower resolution and limited ability to extract information from the environment. Conceptual approaches, on the other hand, are subdivided into a wide range of categories, which include scene analysis, visual odometry or localization, and cooperative perception. Robotic scene analysis is still far from human scene analysis, where no solution has yet been proposed to simultaneously and convincingly tackle the segmentation or classification of objects, distractors, and any other secondary entities to the task. Visual odometry, simultaneous localization and mapping or SLAM, or generally even only localization is still far from being a completely solved problem in dynamic environments. Methods are still unable to completely cope with the dynamic objects under the dynamic circumstances at stake. As for cooperative approaches, there are many challenges still to be solved, especially when dealing with distributed multi-robot systems. While many standards are already in place for inter-robot wireless communication, these have limited bandwidth and range. Furthermore, cooperative perception is greatly affected by all other issues affecting individual perception as well, namely localization. Without proper localization, cooperation is sort of meaningless. As stated before, different types of sensors are affected differently, and they all depict certain weaknesses in extracting information from the environment, be it due to their susceptibility to environmental noise or because they do not offer the needed resolution or range of information. This means that single sensory modality is inadequate to give a robust estimate of the state of the robot and the environment. The combination of different sensors, when done properly, is, however, a promising approach, with the intent to combine their benefits and mitigate their limitations. It is not new that intelligent robots require a considerable amount of onboard sensors, often of multiple modalities, in order to operate consistently. The Ranger is not an exception, comprising 2 3D lidars, 1 multispectral camera, 1 thermal camera, 4 depth cameras, and 1 GPS module with real-time kinematics and 1 IMU. The combination of the data collected by these sensors requires a transformation or projection of data from one sensor coordinate frame to another. Our approach has been seamlessly integrated with the ROS framework, allowing to deal with data association, be it through extrinsic calibration or manual assessment. Both sensors' placement and subsequent projection of the data from their coordinates to the robot was a critical step in the design of a filter, which fell on Kalman-based approaches. Generally speaking, Kalman filtering uses a series of measurements observed over time and from different sensing modalities containing statistical noise and other inaccuracies, and produces estimates that tend to be more accurate than single measurements alone by estimating a joint probability distribution over the variables for each time frame. Among the many Kalman filtering variants, the extended Kalman filter, or EKF, is the nonlinear version of the Kalman filter, which linearizes about an estimate of the current mean and covariance. In robotics, as in other domains, the EKF has been considered the de facto standard in the theory of nonlinear state estimation, navigation systems, and GPS. Despite this, it is important to state that the EKF is not an optimal filter, but rather it is implemented based on a set of approximations. This means that, unlike the traditional Kalman filter, the EKF may diverge if the consecutive linearizations are not a good approximation of the linear model in all the associated uncertainty domain. Nevertheless, as most systems are nonlinear, traditional Kalman filter is not even an option in the first place. This multimodal architecture has first been tested by deploying the Ranger in an unpopulated and unpaved road with surrounding vegetation remotely operated from inside the cab, with the intent to extract as many datasets or ROS bags as possible for subsequent analysis. Several ROS packages have been tested, configured, tuned, and combined, wherein Cartographer, Robolocalization, and Octomap played a central role. Several experiments have been conducted to test the relevance of the different sensors in estimating the pose of the robot in the field and how each of the sensors affect the overall performance of the system. Both estimated trajectory and map generated by the robot were highly accurate, which allowed to go down the rabbit hole a little bit more. Instead of mapping general physical properties of the scenario with octrees, we have explored how to properly combine the elevation mapping and the traversability mapping ROS packages. The elevation mapping ROS package has been designed for navigation tasks, hereby improved by using the pose estimator and the multimodal sensing architecture previously addressed. The provided elevation map reflects the pose uncertainty that is aggregated through the motion of the robot. Subsequently, this map feeds a second layer, the Traversability Mapping ROS package, which has been designed to estimate traversability in rough, non-planar terrain, which is not a straightforward task. The traversability of the terrain is estimated on the basis of a discrete 2.5D elevation map, wherein the terrain characteristics, such as slope, roughness, and steps, are extracted by applying different filters on the elevation map previously generated. To assess these new developments, the Ranger has been deployed in a new scenario that would allow for larger mobility. At this stage, the Ranger was remotely operated from outside the cab, which is later explained in this video, with the intent to assess the traversability of the terrain, which, as it can be seen, it continuously varied between fully traversable and hardly traversable or not traversable at all, from cold to hot colors respectively. You probably noticed that top left rectangle there, and you might be asking what this is, right? Well, this is exactly what takes us to the next step, semantic segmentation. As noted, so far, autonomy has not been reached yet. First, we were driving the Ranger from inside the cab, and then we were operating it from the far. For autonomy to emerge, the robot needs to be able to extract meaningful information from the scenario and act accordingly. For that to happen, it needs to go beyond estimating its pose, analyzing the traversability of the scenario, or even mapping it. It needs to contextualize the data it sees. This is where semantic segmentation comes in. For simplicity, we could say that semantic segmentation is like an upgrade over classification and object detection. For instance, methods for classification plus localization, or image localization if you want, allow to not only identify objects in an image but also their location. In case we have multiple objects present, we then rely on the concept of object detection. However, before detecting the objects and even before classifying the image, we need to understand what the image consists of. This is where semantic segmentation is helpful. Images are not more than a collection of different pixels which are grouped together based on similar attributes by using semantic segmentation. Put it differently, well, we could say that semantic segmentation models sort of like create a pixel-wise mask for each object in the image, providing a far more granular understanding of the scene. As expected, deep learning methods are key for this to happen with the envisaged performance and in real time. Several architectures have been evaluated in the Ranger, but the Bonnet-All package showed a particularly promising result, especially for the semantic segmentation of forestry fuel, or putting it differently, to identify where removable vegetation is so that the Ranger can remove it. Several experiments have been once again conducted, this time under different scenarios and with slightly different vegetation. Training was painful since all labeling needs to be handmade, even though many tools are available that facilitate our job. For this reason, only a few hundred images have been used for training. Nevertheless, despite the small dimension of the training dataset considering deep learning standards, the results were still promising, identifying the ground vegetation to be removed by the Ranger in most occasions. Yet a few undesirable detections or false positives have been observed at the time. Currently, progress has been made by exploiting transfer learning approaches and hyperparameter optimization. As scene perception is then responsible for providing a representation of both world and robo, which is often noisy though necessary to extract affordances that should be fed to a decision-making layer which should select the most optimal goal and task-oriented affordance. Computational resources are crucial so that these decisions are made in a time-efficient manner. In a way, when addressing action in robotics, most of the time we deal with challenges inherent to the field of control theory, which received plenty of attention from roboticists over the past 2 decades, to say the least. Large companies such as Boston Dynamics are a living proof of how advanced control systems are. However, most of those actually lack the proper perception-action coupling, often mostly focusing on control and not really on the needed feedback to execute these routines under non-supervised environments. Because field robots are supposed to operate in uneven, inhomogeneous and muddy environments and to often manipulate non-rigid bodies, and all this taking into account human populated environments, safety and fault tolerance are also key to their successful deployment. During the development of the Ranger, as previously addressed, most of the actuators were already built in as part of the human-operated commercial machine. These include electric and hydraulic motors, yet feedback is key. And this does not only imply exteroceptive sensors as the ones previously adopted for perception, but also proprioceptive, or put it differently, sensors designed to measure the inner state of the robot. The inclusion of encoders, inertial sensors, and inclinometers has been contemplated so that the Ranger is more self-aware, acting as critical components of the decision-making layer. These later fell on the use of state machines, the most common ones known as finite state machines or FSMs. An FSM is one of many mathematical models used for computation, including decision-making systems. The FSM can change from one state to another in response to some inputs. A lamp that is currently in an off state is turned on by pressing a button, which triggers a transition to the on state. Regardless on how the many types and variants of state machines, robots are intelligent systems that often resort to these models. It is unarguably that those models are very simplistic indeed, though still quite powerful, especially when combined with more advanced AI approaches. Let's take autonomous driving as an example. Even some of the most recent papers on the topic resort to FSM-based approaches. In the DARPA Urban Challenge, one of the most well-known competition on autonomous driving, the Stanford junior team succeeded in applying FSM with several scenarios in urban traffic roads. This does not mean that the FSM on its own is capable of dealing with all the challenges found in the real world. However, states within the FSM can be significantly more complex, adopting other models, including other FSMs on their own, which can be transferred to other domains as well and integrated in other FSMs. For instance, we have developed our own follow waypoint state, similar to what can be found in autonomous driving or even unmanned aerial vehicles, though we have applied for autonomous solar panel cleaning. Naturally, the follow waypoint state is more than a simple state. It is rather a collection of other states connected by transitions that are triggered depending upon many conditions. For instance, if the robo is deviating from a next predefined waypoint, it should start rotating towards it, or if the robo sensor senses that it might be near from jumping off out of a solar panel, then it should enter a new state built to deal with this recovery mechanism. Be aware that FSM are far from being exclusive to robotics. Those have been adopted in many other domains, being games one of the most common ones. For instance, the Shambler monster from Quake has a little bit more than a handful of simple states. For instance, it spawns and enters an idle state. While it doesn't detect the player, once it does, it enters an attack state, which can end in re-attack, which is the most common one since the monster charges the player swiftly, or a missile attack in case the player is able to stay away from his melee range. Ultimately, either the player dies or runs away, which renders the monster useless on its idle state, or the monster dies. The fact that the behavior of state machines in modern society is noticeable and computationally efficient made this the right model for the Ranger. Even though its FSM is still under construction, the Ranger can already choose from an interesting range of possibilities, depending on specific inputs triggering the transitions between states. The most obvious state is the one that enables the user to gain full control of the machine using a remote controller. Transition to this state is made at any time, as long as the user triggers the teleop flag. Entering this state bridges the existing teleop ROS package with the J1939 inner protocol of the machine, allowing the user to control linear and angular velocities of the Ranger in real time from the far, just like from the inside the cab. The fact that the FSM moves to this state whenever the user requests it to is crucial, since it provides a way to safely interrupt undesirable situations from happening during fully autonomous operation. S-Bus Radio Serial Communication Protocol has been adopted since it is able to support up to 18 channels using only one signal cable. The S-Bus is an inverted UART communication signal, and while other protocols could be adopted, the S-Bus is 3 times faster than most alternatives, including CPPM and PWM, being ideally suited for fast interaction with the machine. Remote operation seems pretty straightforward and far from the end objective, which is for the Ranger to be fully autonomous. Furthermore, if the plan is to remove vegetation from unknown scenarios, then some sort of reconnaissance should be targeted. This is where rapidly exploring random trees fall. For the Ranger to efficiently operate in forests, it requires a map of its physical properties, which include vegetation to be removed. Autonomous exploration strategies often direct robots to unexplored space by detecting frontiers or boundaries separating known space from unknown space. The RRT algorithm has been chosen since it is biased towards unexplored and unvisited regions, thus ensuring complete map coverage. The Ranger integrates the RRT exploration ROS package, endowing it with the ability to use multiple RRTs. The proposed strategy has been implemented and tested under both simulation and real-world experiments, and while current efforts aim solely at the Ranger, the extension of the exploration approach to multiple robots is inevitable in order to contemplate for other agents as well, namely UAVs. Here the principle is simple. After specifying 4 points as exploration boundaries, the Ranger starts its exploration routine, defining planning routes by taking into account the traversability analysis previously addressed. It is then only a matter of time until the robot is able to provide a reliable representation of the map, which can be subsequently be fed to a new behavior, targeting, for instance, vegetation management. The bottom line of this video is that field robotics is the most challenging subdomain of robotics due to the need to operate in unstructured and unknown challenging scenarios. Common areas of application remain construction, agriculture, and forestry, though space robotics and underwater robotics are very good, extremely challenging examples as well. The perception-action couple is key. Perception deals with the noisy nature of these environments with the intent to provide affordances to the decision-making layer, while action requires the robot to select the most optimal affordances and execute it under harsh and uncertain conditions. This video presented a series of contributions led on Forestry autonomous machine built as an extension of an existing compact track loader. Such an extension started by understanding how components within the machine communicate with one another so that a ROS-enabled CPU could be integrated in the loop. A series of contributions around perception and action have been delineated to tackle existing challenges. These have been evaluated on the Ranger under different simulation and real-world experiments, leading to an increasingly matured autonomous solution. And this is it. I expect this video offered insights on the guidelines we have been following for the development of affordable field heavy-duty robots. The results achieved so far provide evidence that these guidelines can offer substantial benefits over in-house built robotic solutions. Thank you so much for your attention and see you soon.